So good morning, ladies and gentlemen. I'm really honored to be here, and I would like to thank the ISSCC committee for inviting me here to share with you our vision about the brain-inspired technologies. So let me start the talk with a brief journey into the understanding of the brain and the parallel development of artificial intelligence. So more has been discovered in the last decades about the human brain than in all prior human history. And neuroimaging has shown that the brain is a highly interconnected organ. And in particular, these precise brain wiring maps have been obtained thanks to the use of a new magnetic resonance imaging, which is named diffusion tensors, and use the water diffusion in the brain. Neuroscientists have recently revealed that there is a global communication across the brain. These results have been obtained in Neurospin, which is a research lab in Paris, completely dedicated to the brain study, essentially based on neuroimaging. Here you can see experiments obtained with high-density electroencephalography on awake patients which recover from coma in different states of consciousness. And in particular, what appears is that the global neuronal communication systematically increases when the conscious state increases. In particular, aside distant area in the cortical and thalamic areas. This indeed supports a theory of distributed processing in the brain. Non-invasive techniques, imaging techniques, has also allowed the neuroscientists to study for the very first time the development of the brain neuronal organization in children. What appears is that the brain is inherently very well organized with a complex architecture from the very beginning. And it will take about 20 years for all the connection to become fully mature. But this will happen with different rate of maturation for the different functional areas. What is amazing is, for example, that learning to read is an ideal example to express the brain plasticity. MRI have shown that reading is a collective activity which involves different areas in the brain, in particular the vision and spoken languages areas, which are indeed activated already in 2-month-old infant when they listen to the mother language. But there is a specific area, a very small area in the brain, which is named the visual word form area, which is activated when we learn to read at the primary school. And this area is very important because it acts as the interface between the visual and the spoken language. So in this case, the brain plasticity corresponds to reorganize, connected, already existing algorithms. So, but the question is, what does it cost to an organism to operate the brain with all these functionalities? So we know that the brain is about 2% of the body's weight, but it's 20% of its resting metabolism. So from the body perspective, the neuronal activity is quite expensive. And recent studies have shown that the brain organization has been shaped during the evolution with the trade-off between a parsimonious principle of minimizing the cost while maximizing the adaptive value and robustness. And minimizing the energy cost has been done through the optimization of the neuronal codes, the wiring patterns, and also introducing randomness. So at the end, the total energy budget for the brain is about 20 watt, which is indeed extremely energy efficient compared to any cognitive computing systems. Let's come now to the parallel development of artificial intelligence, which indeed, at least in its early stage, has been very much inspired by the discovery in the brain. So artificial intelligence has been discussed publicly for the very first time at the Dartmouth College conference in 1956. And we know that in recent years, the boost in performance and application of machine learning has been driven by two main factors. So first, the dramatic increase in computational power of modern computers, in particular the introduction of parallel computing. And secondly, the availability of a huge amount of data, thanks to the Internet of Things, which has been essential for the optimization of the learning and training algorithms. Among the different fields of machine learning, deep learning is definitely the most popular. And thanks to this technique, we know that tasks which were seen as impossible before are now successfully tackled, like, for example, the natural speech recognition or complex game. A remarkable example is the AlphaGo Zero from Google, which is an example of how performance can be improved by refining the algorithm architectures and introducing new learning technique as reinforcement learning. So the application of artificial intelligence are today pervasive in the era of ubiquitous computing. And the remarkable examples are the autonomous vehicle, the smart homes, the cloud control, the financial service or smart health, and so on. And each one of these applications rely on a particular hardware architectures, and for analysis and transmission rely on an element of the hierarchical structure of the IoT infrastructure. So it could be end devices or wireless sensor network, edge or fog layer, which is a hub between the end devices and the cloud layer or the cloud service. Today is particularly important to distribute the intelligence all over the whole network. And this for a number of reasons. First of all, because, for example, in the case of autonomous car, safety requires local decision in real time. And the same for privacy, for example. Privacy of personal data, like in the case of systems which can detect the faults in private home, need that the data will be analyzed and treated and selected before being transmitted. So distributed intelligence can really address also bandwidth issue and diminishes the communication cost. So it's very important to develop a new, let's say, low-power technologies that can bring the artificial intelligence as close as possible to the edge and end devices layer for the future application. So this picture illustrates the current hardware and technologies using machine learning as reported by Bohr Insight and Strategy. And essentially what we can see is that all the technologies here illustrated needs a training and inference to implement deep learning. So the training correspond to an adjustment, iterative adjustment of the weighted connection between the neurons by using massive amount of data. And usually is done with the supervised learning, which means that the learner is provided with a target by an external teacher, which suggests what should be the answer. And usually training is done in the data center on farms of GPU, and it could need several weeks, and it's extremely power consuming. So this is one of the elements which is seen as a possible issue for future development of machine learning. The second step is the inference about new data by using trained networks. And this could be done in data center, edge, or on devices, and it could be done on CPU, GPUs, FPGAs, or specially built ASICs. And obviously, this depends on the application and on the environment. So main industrial actors to address the embedded market have developed edge platform, artificial intelligence edge platforms, which can run artificial intelligence algorithm, but in general inference, with embedded hardware, CPUs or GPUs. We can see here in this graph, which illustrated the computing efficiency, so in GOPS per watt, as a function of the computing performance in GOPS, how Intel has leveraged the Moore's law and architecture improvement for two of its products, in particular the Movidius Myriad vision processor for drone application and the Mobileye for autonomous car. And we see how the impressive improvement in terms of performance and power, for example, in Mobileye, by scaling the FinFET from the 30 nanometer to the 7 nanometer. Since 2012, also NVIDIA has introduced artificial intelligence product on the market. And again, we can see here the two examples, the Jetson TX and the Drive PX, so the Jetson for drone and robot and Drive PX for autonomous car. And in this case, we can remark that a big improvement in performance while keeping the power consumption even with an improvement has been obtained with architecture solution. So if we take a larger perspective on the same graph, and we introduce not only chips which are in volume production, but also the stage of prototypes, design, or designed by academics, we can see these as target different application fields like servers, autonomous car, drone, robots, or consumer devices. But the first remark is that the gap compared to the performance and efficiency of the human brain still remain very, very large. The human brain has a consumption, as we told before, of 20 watts, but a computing performance of about 10 to 11 GOPS. And the second remark is that there are few hardware that really address the low power market, so below 100 milliwatt. And among them, let's say, remarkable works from academia. And finally, there is nearly no hardware which addressed the ultra-low power market below 100 microwatt, which is indeed very relevant for intelligent IoT devices, which are extremely demanding in terms of power consumption, because they rely often on energy harvesting source or single battery for years. This is indeed the performance and efficiency, for example, of tiny brain intelligent animals like the honeybee. So we believe that it will be hard for traditional architecture to address this very low power technology, very low power area, and that's why we take as a target for new neuromorphic computing this ultra-low power area. So this brings us to the second part of the talk, which is about how advanced technologies can be really a player to make neuromorphic hardware a reality.
LETI is a world-leading micro and nanotechnologies research institute located in Grenoble, France. Inspired by the human brain, whose computing efficiency and low power performance still remain unmatched, LETI is developing novel neuromorphic systems using optimized emerging CMOS technologies. The brain and spinal cord form the central nervous system. The brain processes and coordinates the body's activities using information from the sensory receptors. Neuroimaging has revealed a multi-layered brain structure with an outer, reconfigurable cortex area and subcortical hardwired core. The cortex is composed of a very big number of large-scale neural networks, arranged hierarchically in horizontal layers and vertical columns having dense modules and sparse overall connectivity. Neurons are the elementary building blocks of neural networks. They communicate by way of action potentials, or spikes, which propagate along axons and accumulate in specialized regions called synapses. Transmission across the synaptic gap is accomplished by chemical messengers, called neurotransmitters. Connections between neurons are altered in response to a stimulus. The persistence of these alterations is the biological basis of human memory. Learning requires synaptic plasticity, which refers to the capacity of change in the synapses structure. Inspired by neuroscience and the functional principles of the human brain, Leti's scientists are developing innovative low-power systems by implementing optimized special-purpose hardware fabricated on 300mm wafers. Novel emerging technologies are being used for the synthesis of smart systems. Artificial neurons are being manufactured using specialized CMOS circuits based on fully depleted SOI technologies with a mixed-signal design approach. FD-SOI technologies, pioneered by Leti, have proven to be suitable for ultra-low power design. Non-volatile resistive memories are promising components to simulate synaptic behavior. Leti is developing resistive random access memories, such as phase change memories, conductive bridge memories, and vertical oxide-based memories. The variation of their resistive state enables information storage. These technologies offer non-volatility, precise conductance modulation, and high density of integration needed to model synaptic behavior. Based on the columnar organization of the brain cortex, Leti is integrating FD-SOI circuits and resistive memories monolithically, using an extremely dense 3D integration technology called CoolCube. Active device layers are stacked sequentially using very low thermal budgets. This makes it possible to obtain very small 3D contact pitches of the order of 100 nanometers within and between the different tiers. Less dense 3D integration is also possible with more technologies, such as through silicon vias coupled with hybrid bonding techniques. These allow for high parallelism and energy-efficient computing. The use of photonic waveguides to connect networks across long distances offers high speeds, high bandwidth, and low crosstalk. The central nervous system is connected to our senses: seeing, hearing, touching, tasting, and smelling, and to our emotions, thoughts, and memory. Similarly, extremely low power, context-aware, multi-module platforms with spike-based neural networks can be directly interfaced to bio-inspired event-driven sensors for image, audio, tactile, and chemical sensing. Brain-inspired hardware, coupled to new computing paradigms, will exploit the full potential of new disruptive technologies and address the enduring power efficiency issues of traditional computing architectures. Distributed intelligence will span the whole IoT network, sustaining our hyper-connected society and benefiting individuals worldwide.
So this video illustrates how the understanding of the brain can be really a source of inspiration to design and develop really low-power, fault-tolerant, and self-adaptive neuromorphic hardware. So let me give you now some more details about the theoretical paradigm which are the basis of neural network. Neurobiology has shown, first of all, that time is really the critical parameter in computing process in the brain. And this is the main hypothesis of what is called the third generation of neural networks, essentially the spiking neural networks, which use spikes for communication, for computing, and for memory and learning. So the communication protocol, which is usually adopted in spiking neural networks, is what is called the address event representation, where an event is represented by the address of the spiking element. Could be a neuron or could be a pixel in an artificial retina, for example. Concerning the spiking neurons, there are different models They differ in the biological plausibility and computational efficiency, and the leaky and integrate and fire model is probably the most commonly used. Another key features is the learning paradigm, and the spiking neural networks are definitely compatible with unsupervised learning, which means learning without any features and feedbacks from the external teacher. And one example of learning rule, which is biologically inspired, is the spike time independent plasticity, where the synaptic weight increases when the presynaptic neuron just spikes before the postsynaptic neuron. So let's see now more in detail the technology which are the building blocks to develop and fabricate neuromorphic hardware. As we told before, fully depleted SOI is one of the key technologies for future CMOS generation. It has been deployed in many products in the market, which are illustrated here, and thanks to its suitability for low power design, can be used for neuromorphic hardware. Recently, a neuromorphic processor named Dynapsel for dynamic neuromorphic asynchronous processor with online learning has been designed by the University of Zurich in the frame of the NEUROM3 European project and fabricated using a 28 nanometer FD-SOI by ST Microelectronics. It counts 4 non-plastic cores, with each one with the 256 neurons, 16K TCAM-based programmable synapses, 1 plastic core with the 64 neurons, 8K plastic synapses, and 8K programmable synapses. And it achieved 320 gigasynaptic operation per second per watt. And each spikes consume about 50 picojoule, which is very similar to the energy efficiency of a biological neuron. So another technologies which is key for the neuromorphic hardware are resistive memories. Again, these exist in different flavors on the market by different companies. And usually they are promising, especially because they are non-volatile, they offer fast switching, high reliability, so they can be used to make the memory coming closer to the processing unit and revolutionize the memory hierarchy. Thanks to the low power and multi-value properties, they can be used as artificial synapses. Here is an example of unsupervised learning obtained with the 2 PCM-SYNAPSE, which has been simulated with an in-house simulator in 2T2 in a fully connected 2 layers neural network with 70 neurons and 4 million PCM. And this has been used to test automobile tracking, giving an average detection rate of about 92% and with the power consumption for the system of about 112 microwatt for learning. Another examples are these OXRAM based on hafnium oxide synapse, which has been simulated in a fully connected neural network, which is able to identify, learn, and recognize different biosignals, so spikes, and without supervised learning. So, and this is definitely very useful for future, let's say, autonomous implanted devices for brain repair. Finally, we have said that the 3D technologies, let's say, really the efficiency and performance of the brain really relies on these 3D interconnections. So 3D technologies are obviously a key enabler for future neuromorphic hardware. Here are illustrated different emerging techniques, so through silicon bias, widely used for heterogeneous integration, but more and more used in many core and high-performance computing. We can reach a pitch of about 1 micron by using hybrid bonding. And the most dense technology, 3D technologies, is what is called the 3D sequential monolithic or cool cube, which allow to reach a pitch of about 100 nanometer, and so coming closer to the interconnection of cortical microcolumn. Here is an example of a smart imagers named RETINE, which is made from a two-layer 3D stack backside illuminated vision chip. And we see that in the top tier, we have an image sensor, so it consists of pixels and in focal plane pixel readout circuits. And in the bottom tier, we have the multi-core parallel processor, which compute the data from the pixel and achieve a very high frame rate of about 5,500 frames per second. As we have said, the 3D sequential monolithic is the most dense 3D technology. And as I wanted to present this work about 3D monolithic nanosystem presented recently by Stanford University, which was applied to the classification of ambient gases. So now let's come to the third part of the talk, which is indeed the future opportunities which are opened by this new ultra-low power real-time neuromorphic hardware. Let me start with this short introduction, which indeed underlines the fact that in recent years there has been the emergence of a new cognitive paradigm, which is named embodiment. This, in some way, advocates a systemic view for the understanding of cognition. This means the idea is essentially that the action shapes the experience of thinking, or in other words, that intelligence emerges by the interaction of an agent with the environment through the sensory motor activities. We can understand that very well if we look at very tiny and intelligent animals, like insects, for example. If we think to the wood cricket is, let's say, renowned for his hypersensitivity and the capability of escape in front of a predator. And this is due to the fact that it has a very filiform sensing hair in these appendices in the abdomen, which are extremely sensitive to airflow. And the other point is that the signal coming from this air are not elaborated in the main brain in the head, but are elaborated in a secondary brain, which is located in the abdomen. So information is treated locally. The second example are honeybees, which have a very small brain compared to the human brain, 950,000 neurons, but are able of remarkable behaviors like sensing, navigation, communication. They live in community and act cooperatively. And it seems that one of the reasons of their extremely capability to live together and communicate is really one part of the brain, which is called the mushroom bodies, which act as the integration centers for all the sensing data. So these tiny animals could be really a source of inspiration for future cognitive cyber-physical systems. And what is the main challenge for this future system? The main challenge is definitely the difference between the artificial intelligence world and reality, which is indeed the different degree of predictability. So the reality is a non-stationary environment, rapidly changing. And how to tackle this feature? To do that, we really need to have a dynamic interaction between the system and the environment. And this could be done by introducing new components in these systems, like smart event-driven sensor networks, actuators, situation-aware multimodal platforms, and low-power spiking neural network processor. And so as said before, for tiny animals, a tiny drone which has been recently fabricated in Leti, the Leti's 360 Fusion, is already equipped with perception technologies and 3D anti-crash solution to achieve a safe navigation. But the introduction of neuromorphic sensor and hardware will allow for high-speed autonomous flight. Another example of cyber-physical system and embodied intelligence are autonomous sensory motor robots. So social robots with a specific and architecture address questions as identity, role, characters, communication, and languages. It is with many trials and with the error, like children, they make sense themselves of the world. So this is the example of the iCube robot, which indeed is shaped as a 4-year child and has astonishing ability in, for example, perception. So another example are the now humanoid robot fabricated in the frame of the European Dream project, which interacts with children and are used for the early detection of autism, for example. So the next step will be indeed to interface the VLSI circuits with the biological system, and this is indeed what happened in the brain-computer interface. So let's see how this brain-computer interface is used, for example, in Leti for rehabilitation purpose.
The BCI project for Brain-Computer Interface is a multidisciplinary flagship project of Clinatec's Biomedical Research Center. Its goal is to increase the autonomy of people with motor disabilities using a compensation device that provides improved mobility. The entire system was developed at Clinatec. This BCI system uses a disabled person's voluntary cerebral motor activity to pilot a 4-limb exoskeleton. It consists of a unique implantable medical device called WIMAGINE, which can record electrocorticogram electrical signals and transmit them wirelessly. Algorithms that decode enormous volumes of data in real time in order to predict the movement that the patient imagines and to pilot the exoskeleton. And an arm and leg exoskeleton built with innovative actuators which are light and have low inertia.
So we believe that in the future, the sophistication of the spiking neural network will allow to have embedded neuromorphic BCI, which means that this low-power embedded spiking neural network will be placed at the electrode site and will allow, let's say, recording and stimulation of the brain in closed short loops. And moreover, this will allow to have a real-time interface to control the prosthetic limb. So the next step and the final step will be really to have a new generation of cognitive neuroprosthesis with bidirectional hybrid network. And this will be used for brain repair in case, for example, of neurological issues or metabolism dysfunction. And so this device will require to be precise, adaptive, and intelligent. Let's come now to the conclusion. So I hope that I have shown to you how the understanding of the brain and also of the brain of tiny animals, not only of the human brain, could be really source of inspiration for ultra-low power brain-inspired hardware. What is really critical in this field is to have an holistic research approach, which means a virtual interchange, a virtual interaction between software and hardware, between neurobiology and technologies. And this will open the way to unforeseen new application, and in particular where there will be a dynamic interaction between the system and the environment. So let me just acknowledge all the collaborators who helped me for this talk, in particular Susanna Bonnetier, Edith Ben, and Marc Duranton. And I hope that you enjoyed, and I would like to thank you very much for your attention.